inductive style of reasoning. And that's the core of theory building. I want to explain this first because these two elements require very different skills. And we versus algorithm are better and worse at different parts of it. So in induction, what we're trying to do is we're trying to derive generalizable features from the specific observation that we have. So it's pattern detection. But with abduction, we're trying to develop more explanations of why we observe these patterns, right? We're trying to explain the pattern instead of just surface these patterns. And these are the two core process of building new theories. And what's the logic behind machine learning, right? So this is actually slides I use for my graduate course. I show like master students, okay, this is basically machine learning. It's a game that we've all played. We look at the shapes and color and we're trying to predict what's coming off. And specifically, we train our machine on something that we have with both X and Y. We try to extract the pattern from the data. And then we test the patterns potentially that we found using also the data that we have. We're just not giving the model Y. So I'm gonna deliver a little bit conceptual machine learning because a few years ago, I didn't know how these things work. So I think it's important that we're on the same page so we can discuss some more interesting things. So the second step, we test the model that we came up with, and we found the best pattern, right? The one that has the highest accuracy in the test data set. And then we try to predict the future outcome here. So we make predictions on unknown wise. So that's how machine learning works. And the reason that algorithms are so powerful and important is because it captures the basic fundamental intelligence of humans. The reason it's called artificial intelligence is because human expertise actually is just pattern recognition. So any type of intelligent behavior in any context, if you're a good student, is because you can quickly abstract the patterns in a research paper and how to even write good research paper. So this is a very interesting experiment, actually, from the early 20th century, where they guided people into a room where there's like a random chess pieces on a table, and they asked participants, back then there were like no phones, nothing. They asked participants to remember the chess pieces in this room, and then they're led to a different room and say, okay, recreate what you just saw. So the difference is that there are people varying in their expertise. Some are grandmasters who play chess, and some are just people who have no idea what chess is. And the difference, though, sometimes the chess pieces are entirely random, but in other times, the chess pieces are placed in a way that are taken out of an actual real game. So what happened was, when the chess pieces are entirely random, there's no difference between the grandmaster and just a layperson. But when the chess pieces came from a real game of a chess competition, the grandmasters remember it significantly more than a layperson, which means that what really differentiates a grandmaster is that they are able to understand there's some logic. When there's logic behind the chess pieces, they know what's going on and they remember more. And that's why we're trying to train machines to do the same, because we're trying to make them more smarter as humans. And a lot of these are done actually in gaming. So what I find the most interesting is in 1959, that's a tic-tac-toe game playing machine. So a lot of the algorithm development actually comes from video game playing. So kudos to video game players. So tic-tac-toe machine was just, an automatic machine. It doesn't really learn anything. Fast forward to 1997, what happened here with Deep Blue's algorithm was that Garry Kasparov was the grandmaster that year in chess. He lost to Deep Blue, and Deep Blue employed a certain type of artificial intelligence, which is basically at every given step, the machine will calculate what's the best way to win, given what's on the board and what potentially could happen. So Garry Kasparov later said, this is an instance of quantity leading to quality, because it's not that it did anything smart, it just has better computational power. And in 2016, that we all know, what happened with the Go match was, it's not about computational power anymore on the spot when the competition is happening. It's more that how the algorithm was trained. It was not a rule-based algorithm anymore. It was fed a lot of games, right? The algorithm itself. It doesn't even know Go's rules. It just needs to observe all over and over all the games. And it extracted pattern of how to win a game. So that's the difference from old AI and new AI. Old AI is rule-based. It's like teaching a child to do long division. And new AI can learn from pattern of data. And that's exactly how we learn and how we come to here, right? So if that's the case, how do we utilize AI's new ability of detecting pattern, right? How do we detect pattern, for example? So I mentioned that this is the part we're going to talk about. So as human, when we do deduction in theory, there are a lot of challenges. So I listed a few. Which option would you choose? All of you. Right. So let's think about low reliability, right? Each individual, we observe the data, which means that we're all watching the same Netflix shows, but we observe very different patterns as each individual because we have different experience, we have different assumptions about the world. That would be very different. And the second is that it's very difficult for humans to detect anything that's not linear. Like, remember when COVID started, it's very hard for an average person to even know how exponential trend works, right? It's very hard for our brain to think even a step further, thinking about interactions and other type of shapes. And finally, we all have this problem of overfitting the data. We want to explain everything that we observe, which also means that we explain the noise in the data as well. So a lot of times the theory that we come up with might be very specific to the context. And this is something that machine doesn't really do. Also, I forgot to say, just stop me anytime if you have a question. Just raise your hand or just speak out. That'll be very helpful for me as well, because sometimes I'm just in my mind and not noticing what's going on. Okay, so how does algorithm does this engage in the same inductive process, right? So algorithm can detect very complex patterns. I don't need to tell all of you here because you're here for a certain reason. You're interested in a lot of computational methods. And we know that algorithm can capture way more complicated patterns in the data that could explain the data a lot better than we do. And it has innate built functions that guard against overfitting or regularize the type of model that it generates, right? So we don't have to tell a machine learning algorithm to say, don't overfit the data. It's always trying to make the best prediction out of sample. And also, even if we use very different models, we can't, if the machine is given the same data, we'll come to mostly very similar patterns. So it's highly replicable. And that could be very useful when we're thinking about theory building. But what we're trying to do here is not saying that, okay, since machine's so much better than us in detecting pattern, let the machine do the job and we're done. So these days, when we talk about algorithm, a big topic is human-centered algorithm, right? So in theory building, I think it's the same thing. I didn't say it's algorithmic induction in theory building, but algorithmic supported. So how does that support come from? We need to know what we're good at and what the algorithms are good at, right? So we're looking at assembly method between humans algorithm and the algorithm's own. And I would say what the algorithm is a lot better at is detecting patterns for all the reasons that we mentioned before. But we do need someone to interpret all the patterns that a machine found in a data set. And that requires a human to do it. So with this general setup, 2-3 years ago, my collaborator published a theory paper where they laid out a few steps that if you want to use algorithm to support your theory induction process, these are some of the things that you can do. So first, we have access to a certain data set, and we want to split the data set into 2 random subsamples. And when we use the machine to detect pattern, we're never going to touch sample 2. Why is that? Because we need to save it for hypothesis testing later, right? We can't say we look at the whole sample and we can explain it so perfectly. We use sample 1 to train model, to do the regular training test split as well. And we'll look for the features that can explain the phenomenon that you're interested in. I think anyone in political science in the room can help us with that as well. As like, I remember in the US now, they have some type of, almost artificial generated for human voters. And then they want to see whether they can predict the voting results a lot better. So basically what it's trying to do is the same. If that's something you're interested in and you want to apply that in your sample of something else that you're interested in, for example, maybe who's going to win Michelin star next year, you can gather a lot of the features of the data and try to make a prediction on that. But the most important section, I would say step 2 and 3, because it does involve a lot of human interpretation. There are so many models that you can choose from. There's so many features. Which are the ones that are interpretable? Which are the ones that actually make sense? Because you probably have way more context knowledge than the machine. Even if it has picked something that has really strong predictive power, it doesn't mean that it makes sense. So one of the examples I always use that, companies now really track attrition rate among a lot of employees. And usually what comes up as a top 1 predictor of someone is going to leave the company is them clicking on the HR policy of how to quit. But it's not useful, right? Like it is a predictor that's important, but you can't do anything anymore at that point if you really want to keep people in a company. So we really need your human intelligence to say whether this variable actually makes sense to be incorporated into the theoretical framework. And then finally, we'll test the model that you have on the sample that you have not touched using hypothesis testing. So that's the 4 steps. And I'm going to share one thing that we've used this as an exercise to see whether we can do something with teams, something I studied, and see whether we can use this more inductive approach with algorithm to see whether it predicts team performance better than decades of research. So team composition is really difficult. One of the big reasons that a team has many different goals. It can be, that's the current NASA mission to go to Mars. That's a team. Restaurant, back kitchen, that's a team. And band and sports team are teams. This is a band called sports team. So I thought that funny. So teams vary so much. So to find the best way to compose a team is quite difficult for human beings. Because we don't look like this. This is the Bremen town story. I don't know if you remember when you were a child. Basically, each animal has its own expertise, and they're trying to defend, this big evil person. But as human beings, we stand there. I don't look like a dog, a cat, a mule. Like you don't know what I'm good at. So it's quite difficult to assemble the correct people together. So what we're trying to do with this project was we want to see combining our understanding of how team works and with algorithm. Can we put together predict team performance better? So we started with what are some of the underlying universal characteristics that we can use to capture human beings. And one thing that has been studied for a long time in social psychology is the Big 5 personality. That's something that has been shown to be quite stable across your lifetime. It varies as a population. People actually become, for example, less sociable over time and less open to new experience over time. But more or less, these are some of the defining features that you can use to when we define different types of people. So we're saying, okay, maybe we can use Big 5 personality as a way to predict whether a team will work well together or not. But what are they working on, right? So one of the features of teamwork involves this is not, let's see. That was, all right, I'll just use this. So we use a task that's called a hidden profile task. The reason for that is hidden profile task is something that involves a lot of sharing information and integrating the information from different people. On the left side, you can see an example if you don't know about this paradigm. Basically, as an individual person, everyone will get, so on the left, the example is that we want to choose the best candidate. So we're hiring a new professor, right? Each person has partial information about these candidates, candidate 1 and candidate 2. But because everyone only has partial information, unless we share all the information, we might make a really bad decision because the shared information say, oh, candidate A is much better, which is blue. But once you shared everything, you'll realize, okay, candidate B is actually the better candidate for this position. The reason that we use this in a lot of experiments to study teams is because it captures these two fundamental tensions that we have in teams, is that we like to share common knowledge and our attention gets drawn to common knowledge very frequently and very fast. So we decided we're going to use a hidden profile task to look at whether Big Five personality can predict the team performance on hidden profile task. Because if that's the case, maybe we can, when we try to build new models, we can find other tasks that also have these type of traits or characteristics, which is heavily relying on information sharing and integrating those information. So the specific hidden profile task we used was actually related to our data set. So for any MBA intro course, most MBA students would have gone through something called the average simulation, which is composed of 6 series of hidden profile tasks. They're simulating for about 1 to 2 hours as a mountaineering team. So everyone has their own roles. Some of them are the environmentalist, some of them, well, one of them is a leader, and there's a medical doctor. So everyone has their own information that they need to share with the team, given the different decision point. So this is exactly what the team is trying to solve, which is whether they can successfully go to the peak of Mount Everest, given the different information that they have. So they have to solve all of the hidden profile decision-making along the way. And we have this data set with us. So what we did is basically this. First, we want to try to do a regular hypothesis testing to see whether we can explain performance at all using research in organizational behavior. And then we're going to try the algorithm-supported way to see whether the predictions coming from that, and we do a hypothesis test on what it identified in the data. Would that be a better approach? So it's more of a competition between the two methods. So the data set came from a few years of MBA students. We have thousands of them that had 600 teams. So we think, okay, this may be sufficient at least to both for us to run hypothesis tests on teams, but also if we were to train models, it can also work. So, and these groups are very nice because they're randomly assigned. It's not like people know each other ahead of time. And we're looking at the specific simulation that I mentioned before, and we're looking at how many points the teams have achieved as an outcome that we're interested in. And finally, at some point throughout the course, they also reported their personality measure because these are students. When they were teaching personality during that session, they also did the personality test. So we have their personality profile. So first, we did something very simple. We looked into the literature and see what type of theories we can come up with. So we know that information sharing is important and integration is important, which means that maybe if the team members are really extroverted, they are more likely to share, as our stereotypes about extroverts are. Probably in this room, very few, but you know, people like to talk, they want to share what they care much less about how other people see them. They also for people who are open to new experience, maybe they're more okay with integrating other unique information other people share because these people are drawn to things that they're not necessarily familiar with. They're more open to that. So maybe these two things are important for the team to perform well. We also think leaders are incredibly important in this case as well, because to be able to create an environment that people feel comfortable sharing their information and also synthesize the different information that are available to the team, a lot of times are on the leader's shoulder. So we think that leaders who are also open to experience might be good at integrating information. If they're agreeable, you know, having a leader is a little bit intimidating sometimes, but if these are agreeable leaders, maybe people are more likely to share. And also a conscientious leader and emotionally stable leader are also very important for very intuitive reasons. So we think, okay, these are good predictors, and we are going to do a hypothesis test on the data that we have. So these are some of the hypotheses that we have, and these are the results. So first, we look at only the team aggregated personality we didn't find the two things that we thought would lead to better team performance. So then we added in the leader's personality, and we still didn't really find anything. So this was our first endeavor. We're saying, okay, so much research has said that these things should make an impact, but they didn't. So we didn't find anything, and if you notice, the R-square is pretty low as well. Why is that happening? So we think maybe because the relationship is not really linear among the predictors that we input into our regression. And maybe across many different subsamples that we collected data, there might be a lot of heterogeneity. So there's lots of noise in the data as well. So we decided, okay, let's try this algorithm-supported induction. So following the steps that I mentioned before, the first thing we did is we split the data that we have into sample A and sample B. And so for sample A, we're using it as basically the help with algorithm, and we become a qualitative researcher. We'll look at what are some of the patterns in sample A. So to begin with, we used the major three families of models: random forest, gradient boosting. We wouldn't say that entirely as a family model, but we applied gradient boosting, and we also used neural network on sample A. And everything that you saw before was inputted to the model, including not just mean, but also standard deviation. Remember, we have the big five personality on the leader and on everyone else in the team. So we have the mean for everyone else in the team and the standard deviation, and we have the gender of the leader as well. And we also have the proportion of female in the team. So this is coming from the fact that we know gender is quite important. In the previous regression, we have that as well, when we look at its impact on team performance. And so the first thing that we found was in the training data set, we did see improvement in R-square, but not a lot of really complicated patterns were really detected using the model. In fact, what we really found was the most balanced model, because we care about both the training and the test data set in sample A, right? Because our goal is to find something that can predict out of sample accuracy really high. The best model we found was actually random forest. It also has a very good balance of, because at some point, we're going to step in and say, okay, what do these patterns actually mean? We want something that's actually interpretable as well. So we gave up on neural networks and the very simple LLS predictions, and we decided to focus specifically on random forest models. So from here on, we decided this is the model family that we want to rely on primarily. So remember, we already started using human judgment, right? We're not entirely asking the models to give us whatever they want and only pick accuracy. We need some reasoning behind why we're picking certain models. And this is not surprising, the fact that we're using random forest. Actually, usually random forest actually predict outcome pretty well and also give a sense of interpretability for humans as well. It's actually the most commonly used in companies these days as well when they want to make HR decisions. So one thing that we thought was really surprising when we ran this model, I didn't show you everything there, but is that leader gender did not show up as a feature at all, a top feature. But we think this is actually something very important. The leader of a gender has been demonstrated to be one of the most important factor in predicting a lot of team dynamics and team outcome. And the fact that it didn't show up doesn't mean that it's not important here. And we are humans, we can tell the machine that this is something important and we want to examine, right? So we decided, even though it didn't show up as the strongest predictor, we're going to mandatorily ask the machine to make predictions using leader gender. And the first step that we want to do that is we decided to build models separately for teams that are led by men, women. And we can see that, as we thought, the pattern is very different for teams that are led by men and women. So we're going to run models separately on these subsamples. And we see that with female-led subsample, a lot of the predictors are quite different from the male-led ones. And so what we did here is that we picked the top features from all the models in the subsamples. And we excluded the overlapping ones because they're showing up everywhere. And we use these features instead to look for the best pattern in sample A. And that's the best pattern that we found. So what this is showing is basically we used all the different combinations of the top 5 features in all the subsamples. We only use them and their interaction terms to predict team performance. And we're looking for something that has high R-square across all the subsamples. These subsamples are not subsamples by gender. Basically, to train a really nice model, you can create many random subsamples, right? You want it to perform well in all the different random draw of subsamples. And this is what we did. We realized the most robust pattern that we found was the interaction between leaders' gender and the extroversion of the team, like the mean of all the other people's extroversion. So we think, okay, this is promising. And we think this kind of makes sense because we found this pattern. The machine is not telling us why this performed the best in sample A, but we think there are good reasons for it. We think women leaders are less likely to be very proactive in soliciting information, right? Women are more introverted on average as a population. So if the followers of the team, the other members of the team are extroverted, this buffers against the fact that female leaders might not actually proactively ask for information. They're going to share it anyway. So we think this might be the reason that team would perform better when it's led by a woman, and on average, everyone else is quite extroverted. So this is important before I show you the results, because every time when I share something like this, people are saying this is just p-hacking, right? You're looking for something. Of course it has high p-values. So first, the reason it's not p-hacking was because we're not looking at the second sample at all. So none of the patterns that were found in sample A have anything to do with sample B. And the second is, when we're thinking about pattern abstraction using machine learning, it's not looking for low p-values at all. What it's looking for is basically a combination of coefficients, right? Which coefficients are important in predicting the outcome? Very often what happens was the biggest predictor that's been found using algorithm has very big p-values as well. So it has nothing to do with p-value. That's not what algorithms are optimizing. So, but when we do statistical tests, all we care about is p-value, right? It can have a very big coefficient, but it doesn't matter. It still could be a noise in the sample that you have. So the goal is very different. Of course, one of the things related to split sample, the more optimal way to do it is actually we should just collect new data, right? Instead of splitting sample. I think that would be a step above what we're doing here. Instead of splitting what we have into A and B, we can use the entire data set, and then we collect entirely new sample of data that half of them are male lead, half of them are female lead, testing exactly in an experimental setting the prediction that we have. That's definitely more superior. But I think this is a very good example of, for theory building itself, something that you can do without even collecting new data. Okay, so now that that's out of the way, this is what we found. So basically, there was a significant interaction when we apply this pattern that we're testing in the sample that we never used. And we can also see that R-square increased quite a bit. And we see this interaction that's showing up here. So what we did in step 1, 2, 3, comparing to the original hypothesis testing that we trained out, there's some things that set it apart. So we're basically saying there is a context here that we're trying to study. We're not trying to predict any teams out there, right? The type of theory that initially we derived come from literature that captures all types of teams, all types of people. We came to a general hypothesis that might not be context specific to this type of team and this type of task. So maybe there's a lot of noise in the subsamples. Because the machine, remember, the algorithm didn't really give us the most complicated pattern either. So it might not be that the pattern was complicated. It's just there's so much noise in the data. It's very difficult for me as a human to realize what's the real pattern and what's not. And now we're able to generate some type of undetected insights. And if, like I mentioned, if at this point I'm convinced enough, this is a great theory, right? I don't need to publish this paper. I can use it as a base for me to look into existing literature, collect new data, do an experiment, and verify this insight. And this is what I believe the biggest strength at this point if we use algorithm to do theory building. Because what I found here, even if you don't believe the empirical side, it's just a theory. But it's potentially a more impactful theory because you didn't just rely on what you read and your pattern recognition, you also relied on machines' pattern recognition. It's a combination of the both of you. So this concludes the first part of what I think algorithm these days can help us do. And I think this is something that is rarely discussed in the current discussion about using algorithm to do social science research. It's not that difficult, actually, if you think about the process itself. Even in a lot of the data, if you're I'm an experimentalist, I do a lot of experiments, and as you know, a lot of the experiments don't work out. So even in data set that you have access to that have no use, you can use it to build some type of pattern recognition model to see whether there's something else that you weren't testing in your data set, and it can help you formulate theory going forward. So before I move on to the next part, any questions at this point? What, any doubt? Like, I don't believe in this at all. What is this nonsense?
I have a small question.
Yeah.
I remember you present a green chart where you divide your sample into multiple samples.
Yeah.
The question is how you decide the number of the sub.
Like here, right?
Yeah, like why you choose like maybe 10 subgroups instead of 5, or why is that?
So we tried different combinations. So I'm using the 10 here because it fits here better. So we tried 10, 20, and 5. The main goal here, I guess in any of these type of exercises when we use algorithm, and when there's noise in any data set, right? The main goal is that you want to make sure things replicate with different types of noise and different combination of noise. So we're showing 10, but I would recommend the best way if you're doing something like this is try different numbers, and you have to make sure at least the pattern that you're interested in should consistently show up no matter how many subsample split that you're employing. Of course, you can say 100 times, 10,000 times, what's the end, right? So I think at least you try some variation and the pattern is sort of stable. That's good enough. Maybe if you split it like 100 times, there are maybe 3 subsamples and 100 subsample that doesn't show up. Even here, right? You can see some of the R-square is not super high. It's like the light blue ones. But the main thing is to convince yourself, okay, the pattern is not only showing up in like a weird sample that you randomly draw. So whether it's 5, 10, 20, it's actually your call. But don't just split it once or twice. That's the main thing.
I have a question, which is, did you observe any patterns that you could not really explain based on knowledge, but then you didn't further investigate it because you couldn't explain it from any knowledge that you have?
Yeah, actually all of these, as you can see, these are the top feature that's being extracted, right? One of the things is basically, it's showing that we actually discussed this a little bit. It's related to 1, 2, 3, 4. Even number 4, yeah, number 4, because we thought, it makes sense. It's basically showing that extroversion, the standard deviation of extroversion makes sense. Which a lot of these we think it's basically saying, okay, some people are really extroverted, and some people are very introverted. That's good for the team. It sort of makes sense in a general sense, right? Like, okay, maybe having diversity is general good for teams. That's a general conclusion in teams literature. We thought it's interesting, but not very context specific. That's one of the things why we excluded it. It's not that it entirely doesn't make sense, but it's not very unique to what we're specifically examining. And something that doesn't make sense at all was related to the one right below. It's also leader gender because it's something we're interested in. So we specifically looked into anything that related to leader gender. And then it's the standard deviation of emotional stability. And we think, okay, that's kind of interesting, but what does having diversity, emotional stability, and having a woman have something to do with team performance? Maybe women are better at managing when people are, breaking down at different rates. That could be, but there isn't a very strong reason for us to believe, at least in the literature that we have access to, that are women better at handling very chaotic emotional situation from other people? We don't know that, even though it's being shown on. So I think there are two things to consider here. One is that, is there any literature backup for what you see in the pattern? And then it's also the other goal, right? Like, are we looking for something that's so general that can be applied to any context? Or are you trying to look for patterns that are very specific to this one? So that's how we selected. And of course, the most important thing is still, it's the most robust across all your set samples. Because in the end, you're trying to ask the algorithm, what are the most robust pattern that I cannot see that you're able to? Yeah, go ahead.
Thank you. This is very exciting because it reminds me of some of the recent discussion about AI-assisted qualitative coding, which I have been reading through a lot because I was at a HCI conference 2 weeks ago, and there are a ton of discussion about how we can use ChatGPT to do qualitative coding. And I think that actually resonates with this part of ML-supported induction process. And what I've noticed from your talk and also from some other discussions is that there is a lot of decision making that goes into this human AI collaboration. And like, for example, in your case, initially I didn't find the big influence of gender, but based on the theoretical understanding like of the researchers, you thought that, oh, maybe gender will play an important role, and you dived in, right? So a lot of the human decision making goes into this kind of collaboration. And this is really exciting because I think this generates a lot of questions, right? What kind of co-decision-making process that we need to consider, and ultimately would lead to a most fruitful AI-assisted inductive process. So I'm not sure if I would love to hear about some of your thoughts in this co-decision-making process, like how under what expenses that you consider the machine's suggestions, and what other considerations that the researchers think that, oh, we need to follow our own instincts, our own theoretical understanding, and do some different exploration. So if you could elaborate a little bit more about that, that would be great.
I think this is a very, very important comment, actually, a very insightful comment. I think a lot of these things in the beginning, when we had machines, we think, okay, our life is so easy now, we'll just let it run and we'll have what we want. So the thing is, I think like a qualitative researcher, right? A lot of the things they make decisions on what type of pattern is important. I think for me personally, I think there are a few things to consider here. I think first and foremost, be transparent about the process. That's the most important thing. Like if you use any machine supported approach to even, labeling data, for example, there are also a lot of decision making whenever we solicit the help of generative AI. We need to be very, very transparent about what we did. And that also means that it opens up the opportunity for other people who might be interested in a different range of activity to embark on the same process, but make different decisions. And I think the second one is, it does have something to do with the specific topic you're interested in. It's someone who, in this case, we think gender is important because the literature keeps saying gender is important, and somehow it's not showing up here. I think that's, to me, we still need to have this mindset even before machine generates something. We should make a prediction on what features we believe are important. And the important thing is not what they think or what we think. It's what the difference. Why are there even differences? To me, the difference is something that's very interesting that opens up both theoretical, endeavors that we should take on, because our heuristic does come from somewhere, right? And why is it not showing up? That's actually something quite interesting. So the gender part, because in the beginning it was already in our hypothesis testing, we put it in there. And that's why when we notice this gap, we think, okay, this is something we need to chase down. If you didn't even come up with anything ahead of time, all you do is dumping the data, creating models, looking for patterns, you would have missed it. So it's still very important to engage our brain, right? To think ahead of time. What are my predictions? And how does it go against the machine's predictions? Okay.
I also have a follow-up question. Like, I'm wondering, how do you assess like how reliable one algorithm would be. For example, one of my projects is using the great topic modeling, and it's quite sensitive. The results are quite sensitive to the hyperparameters that I enter. Like each time, for example, I enter different number of topics. I think the result could be kind of different. And also I tried to add some C in the process, but it's really hard to replicate all the results. So I'm wondering about your thoughts on this.
But this is a very different one. I think any bird related question is actually kind of difficult these days. I mean, you can always try to iterate quite a bit with different number of topics. That's what I do. I don't know if it convinces other people, but I think one of the things is you do need to interpret the topic, right? And then people always have this slight suspicion, how did you pick that? Is it because that suits your goal or suits your hypothesis? One of the ways to do it though is it's possible to have a larger set of hypotheses, but you can only verify some of it, right? So you can change the underlying parameters with BERT. But if you're able to give a discussion on why you even think some things did not show up, either because you're changing some parameters and the effect disappeared, or that when you change something, something appeared, right? I think in the end, a lot of these new approach involve a lot of discussing what you think might be happening. And if you're able to document the process that you're engaging in, it's also very helpful for other people to know if they're saying trying to replicate what you're doing and they're not convinced about your findings, you know how to explain the things that you did not find. So I think it's not just about there is no rule of thumb. And I'm not even sure if there's ever going to be a rule of thumb or when we use more advanced topic modeling techniques, right? Or embedding models. So it's more important to consider both sides of why something is happening and why it's not happening. And I think that's the best we can do at this point. One other thing that you could try is, I have maybe later I'll show just a snippet of it. When you can combine it actually with generative AI and ask, instead of fine-tuning the topic modeling process or the embedding process, you ask it to also interpret the input text ahead of time. To me, the only reliable thing that we can do is we have to iterate. We have to iterate 100 times and see if the same thing shows up over and over again. It's hard to do that with BERT, but if it can be verified by a different source, then I think it makes sense. Say the 3 different LLM models also extracted certain topic that aligns with the number of topics that you chose. I think that's an additional layer that can convince people. Yeah, very laborious. Yeah.
I have a question because I tapped on a lot of like key hacking replicability. I guess I would like to know your perspective on using like pre-registration in studies like this where you use algorithms to support induction.
Yeah, I think registration is very important. People are doing it, but not in a very rigorous way. Like I'm an experimentalist by training, so I know even pre-registered effort are, I would say people don't document as detailed as they actually do when they engage in this process. So I do think it's quite important when we do an algorithm supported theory building, because there's so many decisions in between. And I think one of a useful way to engage in this process is don't think about this as, okay, this is my paper, I'm gonna publish this. Instead, really use it as a way to come up with theories. Instead of using it as a way to verify your theory. So really separate the theory building process apart from the theory verification process. So and then if you've done what you did, and that's the way you came up with the theory, you can always document that very clearly, even post-hocly, right? Instead of ahead of time. The biggest problem is that people think, okay, this is a quick way to find something in my new data set. That's the wrong way to go about it.
I have a question. Because I come from the School of Information Management, we got a lot of criticism that we just drop the noise data and find a pattern of the regular data. But sometimes the noise data is more valuable than the regular data. So how should we deal with this problem?
I mean, you don't have to drop it.
Yeah.
I think that's one way to do it, but I think we're always dropping certain data at a certain point. Sometimes what you can do is you can try putting them back in a more systematic way and see to what extent it changes things and what part of it does it change, right? I think in the end, we're all like, doing trial and error in this process. And noise can be really, really valuable. Maybe there's just noise can be just pattern that hasn't been detected yet. So you can incorporate noise back in a way that's systematic and that makes sense to you. I mean, this is like a very abstract discussion right now, but I think you know it in more detail. So it's okay that certain things have been dropped and that's the conclusion that has been reached. But you have to always remember, it's like studying one company versus another. You cannot apply the same pattern you found at Microsoft and say, okay, Google runs it this way and it's going to work for Google. Always remember that the data you have access to is very specific to that sample. So I think another thing to always remind yourself is whatever findings you find, the criticism, it's okay that there are criticisms, but you also need to know in your heart that this is very unique to the specific data that we're examining. You can't say that it will explain everything going forward. All right, let me quickly go through the second part. I thought I wouldn't even use up the whole time when I was emailing the organizer, but this is very nice. So now let's move on to what are some of the things that we can use algorithms for in the second part when we try to come up with new data to support the implication that we got from the theory supported section. So the first thing is, as an experimentalist, what's I'm most interested in is how can it revamp the currently very commonly used methods in social science experiments. So currently, I do a lot of work related to teams, right? So I study interactions and collaborations. Previously, the more traditional way to do it is we hire if we want to manipulate anything about a team that involves human beings, we need to employ an RA. Or pretend to be the leader and, for example, behave in different ways or say different things, which is really expensive, not just in terms of money, but the time and energy RAs need to put in. And it's not always very consistent. So OB people are very interested in leadership, right? Different leadership reflect in different ways of behaviors, but you can't ask an RA to always behave exactly consistently across board. And also it's very difficult to scale up because we only have this many humans. And if a human needs to be present at any interaction or collaboration, that's going to take forever to get data in. And we also have more scenario-based study to study interactions, but they're not very realistic. They're far from the phenomena that business school researchers do, which is real companies and real teamwork. And sometimes when we only talk about scenarios, we're actually capturing what people believe will happen, but not actually what they're going to do. But of course, these things have been around for like 100 years because they're very easily executable. You need to explain to people why you're using these methods. They just make sense. So now, so this is usually what we do these days when we do online interaction studies. I'm just going to show, because a lot of you here don't do these research. It's like we ask people to join an experiment. We're just capturing our screen, pretending to be different people. And I specifically study creativity. So a lot of things is like, we ask people to come together to write a proposal, to come up with a unique idea. In this case, this experiment was looking at, they're trying to create logos for this fake ocean airline. So they get some information and they come together and they chat. So in the traditional way, people are chatting, they're all real people. And maybe if we want to change something about one member's behavior, we ask the RA to join a group and they chat in a very specific way. So this is the old way of doing things. And then they chat, they submit their proposal or their slogan, and then it's done. So what are some new ways to do it? So I'll show a very simple prototype that we developed, that we involved some algorithm. I don't know if so you have to have your laptop. So I don't know if that's possible at all to do. Should I just type this in the chat? So you can't do it on your phone, unfortunately, this QR. You can get the link to your laptop. I'll give you about just 5 minutes to see what this experiment looked like.
Even link to our original group.
Oh, okay,
So it won't come in.
Yeah.
Remaining like 2 minutes.
okay. You can scan it on your phone and then send it through the phone, that's possible.
Okay, then. So while we are waiting, I really have a very simple question for the first part. Because we are still like doing research and finding the pattern based on like a limited sample. So we may still face the question of generalizability because we probably will have some like potential confounder and bias on it. So how did you like attempt to solve it or like to address this question to the reviewer who was studying? I'm very curious.
Yeah, so one of the things that we made very clear is we think generalizability in social sciences is actually a myth. We really wanted to be able to generalize to other things, but everything that we study is basically the study of a sample. I think for your research, it could actually be easier to generalize, because I think a lot of things that you study, at least when I attended journal club, is a lot more fundamental than business school research. So one of the things that you can always argue for generalizability when you pick the feature itself. So some feature are more complex, some are less. So if you say, I really want to discover a theory that's more generalizable, of course you can tell the reviewer ahead of time, there's an sample constraint. But to help with generalizability, my focus of the features are these. So instead of one context-specific feature, you would even opt for something that has lower predictive power, but has more, implication for other type of contexts. And then if you can show that in a new data set, I don't think we'll have a problem.
Okay.
Yeah.
Sorry, this link doesn't work for me.
Oh, really?
Okay.
That works rather.
So
Okay.
But it can only be, does it work on laptop? No, oh, that's odd. I'll just go to the back end.
I can open it.
Oh, you can read it.
Just use the camera to scan and Control C and we open it on your computer.
Yeah, I think the link works.
Oh,
Yeah, I think the link works.
okay. Just make sure though, you didn't leave out any. That's okay.
I'm sending out another link. It's valid, so you can let's say.
It's okay, you can also just look at other people's, but I'm just trying to show.
Yeah, it's already posted. Please refresh.
I think most of them got it.
Okay.
Yeah. And you don't actually need to be the experiment participant. I wanted to tell you a little bit about, so this is a very simple prototype. We can make it a chatbot. We didn't because we were studying something related to human AI creativity. So we want to see when we see different variants in terms of titles being proposed, how do people combine the title? And do they search more for more titles? Or are they satisfied because they saw things are so different? They feel like, oh, I got something creative. So we have different versions. This is the API version. So basically what it's doing is at the back end, it's calling OpenAI API all the time. And it's something we debated not using a chatbot for now as a first study because we want to see how people entirely react to it. But it's just an example of now we have this new partner in crime. We don't have to have a real person there. So we can study how two people come up with ideas together. But now we can replace one person with a very specific version of a person, right? And the cost is very low. We just need to pay the API calls and consistency. I'm not saying we talked a lot about just now, a lot of the questions related to consistency, right? And it's like, maybe we see a different thing every time. The difference from human beings is that you can check consistency after the data collection is done, and you can check all the calls that were made and whether they looked similar to some extent. It's very scalable. We don't need to have anyone to come up and say, we want to see, oh, if your partner is creative versus not creative, would you react differently? So we don't need to require a human being to be creative or be boring in this context. We can actually change the temperature for OpenAI in the backend for ChatGPT. And then it's a lot more realistic. But when we're saying realism is a thing, I also wanted to say that these days, when I run experiments online, even when it's a group of real people, they don't believe other people are real anymore. I always get the feedback at the end of my experiment, even though I paired only humans together, they're saying, no, that's a bot. So now people are very doubtful about generally their interaction online as participants being real or not. So that's something to think about. And I think that might come up as a problem going forward in our social world. So this is one of the examples I want to show to how to generate a new data set, right? To verify your the hunches that you got. And the second thing is related to data processing. So you will have a lot of discussions about these with different speakers, but and I wanted to go through like a simple how embedding model works, but I don't think we have the time. But the way that when I teach students about what's the best way of thinking about embedding models is basically, again, going back to personality. Everyone can be represented by different types of personality. If you were to capture me as a person, I might have 5 dimensions. I might vary in terms of my personality. And these 5 numbers is basically a representative of me, right? And that's exactly what we do when we do embedding models. Because once we convert a person into numbers, we can see whether I and a gentleman are very similar or very different based on our personality. And we can do that for words as well. We can break it down into almost like a long list of personalities related to that specific word. That's how embedding model works. And that's how we vectorize, right? All of the words can be vectorized in a spatial sense. And that really helps us to do a few things related to text analytics. The reason I want to briefly go through this is because, and this is the most well-known, example of once we vectorize king and queen, you can see it can be calculated using men and women. We can do calculations when every single word is being transformed in a vector, in a string of numbers. It's very useful to do these calculations, and it's also very useful to see the distance among them. How is that useful? So the main thing I want to deliver here is that there are different things related to text that has nothing to do with the technical methods itself. It's what text in general represents in this world. So I think there are 3 main categories when you think about applying it to your research. So anything I'm saying here, of course, you can find the code, do the same thing. But what I think a smart PhD student or researcher can do is you can think about these methods and you can think about 100 different ways of utilizing it to capture different type of concepts instead of replicating what someone else has done. Then you really need to understand what's the conceptual understanding behind text analytics, right? So what text actually mean in our real world? I think there are 3 main categories. One is that it basically delivers a characteristic that's showing up in a text corpus that you have access to. It can be online review, it can be online discussion. It's just capturing what this text kind of look like. And what you can do with that is you can compare, are people discussing the same thing in a similar way or in a very different way? So we don't even need to know what they're talking about. It's basically a representation of a text corpus itself. And the second big category is related to topic modeling. A lot of you are more familiar with that. Is we can understand what people are paying attention to. So instead of thinking about topics as what people are talking about, because you do need human interpretation there, if you have an underlying distribution of all the topics, what you really are getting at is for each single person or each group of people, what are they paying attention to the most or the least? Are they paying attention to the same thing? So that's what topics are actually showing. To what extent am I putting in an effort and time into discussing something? And lastly, I think texts are basically reflections of different personas. We are exactly what we say and how we behave. So if you have text about, if I have your diaries and if I have all the text that you have generated over your lifetime, I basically can capture who you are as a person. So these, I think, are 3 main categories when you think about using text analytics in your work. So the first category, just the characteristic of the text itself, without even knowing what the text is, why would that even be important to a researcher? I'm going to show you one example, and we don't have that much time, but what I really want you to get from this is my example. What are some of the things that you can use exactly the same thing, but to capture in a different something else that you're interested in? So for me, something that's very important to use algorithm to capture is because I study creativity for groups. I want to see how is a group's output creative versus not creative comparing to other groups, right? So in one of the studies, what we did was we're asking the groups to interact in a way where you can talk to everyone versus you can only talk to the leader. And then as a team, they came up with a proposal to create an icebreaking event for a company. And they submitted the proposal. And what we're really interested in is by putting people in two different communication circles, will they be able to integrate ideas differently? But we don't want humans to read it. So instead, we want the algorithm telling us what are some of the characteristics of these chats that people generated and the ideas they submitted. Do they look similar or different? So basically, we have this measurement of integration of idea. You can see the chat. So that's what people did when they were chatting and trying to write up the document. And what we're trying to calculate is the cosine distance between the chat, things that people discuss, how far or close it is from the actual discussion, the actual document they submitted at the end. The assumption here is that the closer they are, it means that the more ideas they've taken from the chat and integrated it well into the final document. The more far apart they are, it means that ideas are not really integrated very well because things that are being showing up in people's conversations didn't show up in the final submissions they sent to us. So this is a very simple idea of a cosine similarity, but it's capturing what I'm interested in, which is idea integration.
So can you remind me what is the similarity with that to the
Between the chat and the final document. So we take the chat as a separate thing, we calculate it, we turn the chat into a vector and then the document into a vector and see how close they are to each other.
So for this one, probably it's quite low, right? Because they're not even talking much. Are they talking much?
Yeah, this is only in the beginning. I'm just showing an example. Yeah, so sometimes you'll realize people really generate things directly out of their chat, which means that they integrated everything they discussed. These people, they can't really talk to each other face to face. Like it's set up in a way, all the discussion was happening in the chat. But in other groups, the submission looks so different and people were not even using each other's ideas because they're basically trying to come up with a document on the document itself. So you see the idea integration is not done very well. So actually teams that only are able to chat with a leader, they integrate ideas a lot more compared to when they can chat with everyone because their attention span is like, I have 3 other people I need to talk to. They don't even have the time to think about what's the best way of integrating. So if people can only talk to the leader is the person who took the responsibility of actually synthesizing ideas. So you can see, in the end, what we can see is something like this. We can see that the similarity is a lot more closer when it's purple, right? Purple versus when it's really decentralized, when everyone can talk to everyone. So this is something that, yes, I can kind of ask human raters to observe the chat and then say to what extent are ideas integrated. But this is a very quantifiable way for us to observe it in a more, let's say, quote unquote, objective way. So this is like so simple. We don't even need to think about topics at all. We don't need to care about what they're actually talking about, right? It's basically taking the characteristic of the chat and comparing it with the characteristic of the final submission. So this is the first category that I'm talking about. So the question for you here is that, what are some of the things that this can apply to you, right? Another application sometimes I use using cosine distance is I just look at the submission and I see how different they are from each other. The more creative a submission is, unless it's nonsense, they should actually have much larger cosine distance from all the other submissions, right? Because everyone was given the same prompt. If from the same prompt, my group came up with something entirely unique and creative, it should have a much larger cosine distance from the average of the submission. So these are, the harder part is not the methods, is how are you going to use these simple computational principles to apply to social science phenomena. So this is the first category. And the second, of course, it's about topic. And basically, a lot of times what I'm interested in is doing an interaction. What type of topics come up and dissipate in the interaction. So what I do here is basically, I'm trying to capture the process of how people can become creative. Usually we have a process of being divergent. We're talking about so many different ideas, but because in the end, we have to come to certain conclusions to execute the ideas that we're interested in. It's like you brainstorming with your collaborator, but in the end, you have to pick one idea to collect data, to test your hypothesis and write up a paper. So we should see topics coming coming in the beginning, and then they should disappear gradually later. And one way to do it, this is the context of the study that we did. We're looking at whether it would differ if people interact as avatars versus using their face-to-face online. So then we can also, the main reason we did this was also because we can capture everything that people were talking about, right? And we can do a topic modeling. I'm only using it as one example of one group, right? This actually goes back to an older question that we were discussing related to her, and well, she's not in the room now. Basically, in regular LDA, there is also a lot of noise about what people are actually talking about. I have to label the topic, which is very difficult. But we can see a trend, right? We can see how do the topic emerge and how do the different topics disappear. Of course, we can iterate different ways of generating these topics, but the overall trend should remain in a way where in the beginning, there are a few topics. In the middle, we should see the bulk of topic, and then it will disappear gradually. So to help us understand this process slightly better, so this, I'm only using one group because otherwise I can't really visualize anything for you. So this is one group, and we see all of these topics, and we see some keywords for the topic, but we don't really know exactly what they're talking about. So this is a very similar creativity task. I gave you so many different types of creativity tasks. So this one, we asked them to come up with travel accessories. It can be like a nap, a new type of suitcase. So this is what they're discussing basically. But you can also ask ChatGPT to say, read through the transcripts of these type of Zoom interactions. It's like 15 minutes of transcripts, and tell me what in different stages people are talking about. You can use that as a benchmark to slightly understand the topics better. So in this way, we then go back to topic modeling, and we want to see how to what extent people are contributing to these different topics as well, right? The main goal is that there are these topics that came from different people. How did they come together? And which speaker actually has the most influence in the process? Because then most people will be talking about what that speaker is talking about. So these things are traditionally actually measured just by surveys. So in traditional way, after people interact, they fill out a survey and say, who's the most influential in the team? And what do I still remember the topics that we talked about during my team discussion? So all of them are captured by skill. We want to capture them in the wild, basically. So then after some ChatGPT fine-tuning, we know that there are these different stages, and we can see among all the speakers who are the ones contributing the most during the whole time and for each type of topic. And we can even dive into the specific stages of topic across the different speakers if we want to. And then, of course, we can aggregate them. For example, this group was thinking about something related to voice recognition. So they spent a lot of time discussing voice recognition, and we can see that speaker 3 is the one who's contributing the most. Of course, in the end, we will normalize the time, because influence is not just about the amount that you say, right? It's about even controlling for the amount someone spoke. Are people actually listening to this person's idea? So we can see what's going on during the team process. And then we can also see the type of topic that's been emerging over time. So all the x-axis are just timestamps from the transcripts that we got. And so in this way, we can also look at, I've been consistently showing you one example of one group that speaker 3 really contributed the most. And if we normalize the topic, what topic was showing up here and brought up by this person the most? And again, if we think about cosine distance, right? What I can actually do now for the next step is, does the final idea reported by the group, is it closest to speaker 3? If it's closest, then we know, oh, speaker 3 did have the most influence in the group because the document reflects speaker 3 the most. So the interesting with a lot of the text analytics is that you can find so many places to apply them if you really understand what the underlying logic of the analytical tools are. So this is one way to capture team collaboration and interaction that I think could be interesting to you as well. If you look at, especially some of you look at online discussions, right? How does a topic emerge through timestamp over time? Which person got picked up? For example, you use Reddit data. Why did someone become more influential in directing the whole conversation on Reddit? So these are some of the ways you don't even need to know what the topic is, but you can identify the most influential participator online. And then finally, I'm not gonna go into this. This is actually entirely done on ChatGPT. So this is something I want to introduce to you because I think these days when we think about generative AI, we think about operationalizing our variables a lot. But one thing that's incredibly interesting is I mentioned that everything that we do these days, all our behaviors are captured by how we talk, right, online. So I'm just gonna show you this one last thing. That's something I thought was quite cool. So we have these data that were scraped from Glassdoor, which means that we have, let's see if I show this. We have everyone's review about a company, which means that the things that they really wrote about are things they care about, that they write about their work. So you can basically say, if you feed it into, this is even the older version before 4.0, this was ChatGPT 4. I gave ChatGPT all the reviews written by real people. And I want to see if I were to implement an intervention, do an A/B testing in this company, what would be the most effective A/B testing to make people happier? So what we can do is I can tell ChatGPT, these are the reviews. I'm only going to show the most important thing, and you can actually use that for generating small thought experiments with ChatGPT before you run an actual experiment ahead of time. So the most important step is here. I want to forecast how employees in this company is going to react to some things I'm going to do. I wanted to implement either a work from home policy or a well-being yoga program. And I want to see how employees will react to these two in terms of will it actually make them happier? So because ChatGPT has access to all the qualitative text data that these real employees wrote, right? So I'm telling it to create fake employees based on the persona of each person who wrote the review. So here is what I did. Started by creating a synthetic meta personality, Jane, who values positively all the topics you've uncovered. So I've told ChatGPT to use LDA to uncover topics that have been discussed across all the real employees. And basically, Jane is a generic person. Jane loves what everyone loves, and Jane hates what everyone hates. But how do we create unique employees based on Jane? Then I combine Jane with every single reviews that were written by the real person and say, combine Jane with row A, with employee A, combine Jane with employee B. So Jane then takes on this extra personality that fits into every single real employee. So I create a synthetic participants in my thought experiment. And then I tell ChatGPT to use this panel of people. I also split the panel into two, these fake employees into sample A and sample B. And then I show these people in A, the work from home policy, and show people in a B, the wellness policy. And basically these fake people will react to this intervention I'm about to apply to the company. And I can actually ask ChatGPT to say, give them these policy and ask them to rate on a scale from 1 to 5 how happy they are with the policy, and do a t-test and see which policy will actually potentially work better with these employees. So I think this is a very fun way to think about if you ever want an experiment, and if you have text data that were collected from previously failed experiment that people wrote about something, you can actually regenerate participants ahead of time and see whether your experimental stimuli would actually work on these group of people. Because as long as you have some chunks of text that people provided about themselves, about what they care about in the world, you basically have a way of regenerating these people in a synthetic way and imagine what their future responses are going to be. So I think that's really cool about generative AI is it helps you to use your training data set a lot more effectively when you think about experiments in the future. All right, so this is the last I will talk about. So this is something that we covered today. I think these are interesting things to at least ponder when you do your research from now on. I don't think algorithm is simply just about scraping data more efficiently and labeling data or labeling topic more efficiently for you. It can help you discover the world in a very different way. Because the way that our brain works is exactly how algorithms are created, right? The reason that we make predictions is because we have our input data. It can come from the literature, theoretically. It can also come from your experience, how you grew up, and what type of people you interact with. And you want your algorithm to get better and better over time. And the way we build models can also apply to how we can be better as researchers, because we want to diversify our training data set as well, not just the people that we collaborate with, but also we can use different types of machine learning models to help us think about the world in many different ways that you just have no access to those training data because we are who we are. And I think the second thing that I want to conclude this presentation with is, in the very beginning, when I started doing computational related work, there's one thing that always bothers me is that I don't know what skills I need to acquire and to what level so that I can comfortably do research. And at this point of my life, my current temporary conclusion is that I think you should put that pressure off a little bit. You don't need to be the most technical person on your team. In fact, a lot of the work I've been doing are with second, third year undergraduate students for my RAs. What's the most important thing I think you should really, whenever you see a new method, is you don't need necessarily to know how to code, but you really be very clear about what are the conceptual foundations behind that method. You don't need to be able to replicate the paper, but you want to be very sure about why is this computational method able to capture what they're capturing in the paper. So don't feel really pressured to be, maybe some of you know Copil, be the Copil on the team, right? Like it's very difficult. I will never be her. But what I will do best at is actually I will learn how to communicate with her, understand how she approached things and why she made certain decisions that she did. So you don't need to be the technical person on the team, but you need to be the best translator among everyone in the team. And I think that's what I learned as I tried to, be a more computational person, but still remain a social scientist. All right, thank you.